Hello and welcome to the SimScale webinar on verifying the thermal performance of heat pumps. My name is Dr. Nagman Khan. I'm from the marketing team at SimScale and I'll be your moderator today. I'm delighted to be joined by two of my colleagues, Ajit Kumar and Noor Ozturk, who are from the application engineering team and will be conducting the live demonstration for us today. First, let's take a quick look at why we're holding this event. Well, SimScale, we're empowering engineers to innovate faster and using high fidelity engineering simulation, which is accessible from everywhere and at any scale. And we found that the interest in heat pumps is significant right now in the industry, not just in Europe, but globally as well. And we all know that what's happening with the demand for heating and cooling and the phasing out slowly of fossil fuels to meet our strict carbon, energy efficiency, and climate change targets. So many countries are looking to ban gas-powered heating, and heat pumps have emerged as the main alternative that meets our carbon reduction and efficiency targets as they run on electricity. So today's live demonstration will show users how to quickly set up and run a thermal analysis of any heat pump using performance data supplied by the manufacturer. You will learn how to evaluate the thermal comfort in a room supplied with an air source heat pump specifically. And we're also going to talk very briefly about the benefits of CFD over thermal modeling. Some of you might be using thermal modeling or energy modeling to look at the energy performance of heat pumps and try and look at thermal comfort criteria over a time period to show compliance with various building codes, energy rating systems, and regulations. But the spatial analysis in a room or a space is also important. How is thermal comfort impacted by lower supply temperatures from heat pumps as compared to, for example, radiators from central heating? These are some of the questions we're going to be asking and answering today. I encourage you to have a go. At the end, we'll tell you how to get started with SimScale to run your own simulations. And please do keep your questions coming using the questions pane on GoToWebinar. And we'll take all the questions towards the end. And we'll also send out a link to this recording for those who might not catch all of it or who weren't able to attend today. So I'm delighted now to hand over to my colleague, Ajit, who will discuss the thermal comfort model for evaluating heat pumps.
Thanks, Nagman, for the brief introduction on the application of HVAC systems using CFD. Now let's get into the meat of this session. Here we'll be comparing and evaluating the performance of several heat pump configurations and thereby checking if the thermal comfort is achieved within a system of room or a space that we have considered for the analysis. Let's take a look at why we need to verify the performance of heat pumps. As Nagman mentioned, the heat pumps are becoming a good alternative for the conventional central heating system for your indoor spaces. Understanding the performance of these heat pumps will definitely give a lot of insights about how the indoor thermal comfort is impacted. CFD simulations provides a huge variety of insights regarding the performance of heat pumps, and when we are evaluating the thermal performance of heat pumps, we'll be able to validate if the installed heat pumps are sufficient for the room, or on the other hand, we can also verify certain what-if scenarios, such as how many radiators do we need to actually achieve the thermal comfort of the entire space, or to find out the optimum combination of heat pumps and radiators to make sure we have the thermal comfort of the occupants with a particular design criteria. Just like any other CFD tool, we need a CAD model to start with. So for this case, we are going to take a 3D room with a certain number of occupants, furnitures, and certain other heat generating elements like lights and radiators that contributes to the temperature distribution and hence the thermal comfort of the indoor space. In the next few slides, my colleague Noor will explain a base case with the requirements for the CFD simulation and also project the initial results of the base case.
Thanks, Ajit. Now here we can see the model to be used during the simulations. This setup was prepared as the base case, and by taking the results of this base case as our reference, it is going to be easier and more realistic to have some design iterations and perform more simulations to get closer to our end target. The simulation setup prepared by the CFD expert includes the occupants, which are giving off some heat together with the overhead lights. This simulation setup is based on the winter conditions with zero ambient temperature. Considering the other rooms next to our room of interest, two of the walls are defined as internal, which are warmer compared to the other two walls that the windows are located at, directly facing the outdoors. Similarly, the rooms below and above of this room are also considered to be warmer compared to the outdoor conditions. Finally, for the base case scenario, two radiators are placed under the windows that are facing north and are set up to operate at 60 degrees. Based on the base case simulation run, temperature is well distributed at human sitting level. It's maintained in between 20 to 22 degrees, which is a good room temperature achieved with the help of the radiators in the winter conditions. But the way to assess whether the thermal equilibrium is achieved or not is to check the PMV at human sitting level. As a result of the base case simulation run, the room is observed to be cool for the occupants and further improvement is needed for this setup. As the next step, the design engineer focuses on having some variations in the setup and get closer to the thermal equilibrium condition. This can be achieved by changing the size of the radiators, using different number of radiators, or considering underfloor heating together with the radiators, taking into account that operating temperature of the radiators will be different as the heat pumps are being used. Now, Ajit will continue with the design criteria to be considered during the study.
Thanks, Noor. Now let's imagine the simulation team has found out that the base configuration is not sufficient to be able to achieve the thermal comfort criteria. So they have come back to the design engineer, and now the simulation team is providing the design engineer with a set of design criteria that has to be achieved, and asking the design engineer to make design variations so that we achieve these thermal comfort parameters. In this case, the simulation team is giving the design engineer these three different kind of criteria, such as the average temperature at the human level should be between 23 degrees Celsius and 25 degrees Celsius. Also, the thermal comfort parameter predicted mean OAT at this height or this level should be between minus 0.5 and 0.5, so that the occupants will be thermally comfortable. The simulation team is also putting a constraint on the heat pump output. They want the heat pump output to be less than 60 degrees Celsius. This is to make sure the heat pump is working at higher efficiency. With the details from the simulation team, the design engineer comes back to the design bench. Let's put on the design engineer's hat for now and the rest of this session. So as a design engineer, we try to modify the design, add any other further configurations to make sure the thermal comfort criteria is actually achieved. So to do this, we're going to take three different approaches. The first approach being just a parametric study. In this approach, we are going to take the base case with two radiators and then add a combination of floor heating along with that. So the floor heating ranges from 20 degrees Celsius to 30 degrees Celsius with an increment of 2 degrees. And for the second approach, we are going to make a slight design modification itself. Here we'll be adding two additional radiators on the other side of the room, giving a lot more heat into the indoor space to make sure we achieve the thermal comfort. As a third approach, we also make an additional geometric variation, such as increasing the surface area of the radiators and also adding a double layered radiator at every site. Now we have three different approaches as a concept phase. We would like to validate this using the CFD and see which of the approaches are optimal for this indoor space. Let's go back to the inputs that we got from the simulation team. Along with the design criteria, the simulation team has provided us with a simulation reference project. Let's take a look at this project on how they have set up the base case configuration and then make the changes in the simulation settings to validate our approaches. Before getting into the platform to see how the simulation setting looks like, if you have any questions, please feel free to put that in the chat box so that we can discuss about the questions at the end of this session. Let's open the project that the simulation team has given us as a reference. As you can see, the project link shared by the simulation team takes us to the solution or the results of the base case that they have simulated. Once when the result loads, we can take a quicker look at what kind of results we can extract and what we can improve according to the base case. For example, the simulation team has put a cutting plane at the human head level. To be clear on the position of this plane, we'll turn on the entire space. And now you can see this cutting plane is at the head level of the occupants. As mentioned in the previous slides, we'll be focusing on two main parameters, the temperature at this level and also the predicted mean mode. To check what is the temperature distribution on this level, we'll simply change the variable to temperature. And now you can actually see there is an even distribution of temperature at this human sitting level. To find out what is an average temperature at this level, you can simply click on the statistics and then select the cutting plane that you're looking at. Here we get the minimum, average and maximum temperature at this particular level. As you can see, the average temperature is around 21.2 degrees Celsius. Comparing this to the design criteria, the temperature is a little bit lesser. And hence, the occupants might feel a little bit cooler than expected. We can also do the same for the predicted mean mode. And here the average is around minus 1.9. Minus 1.9 for a predicted mean mode means that the thermal comfort is a little bit on the cooler side. To improve this, we have already three different approaches that we are going to simulate using CFD and validate which of the configuration might actually work out for this indoor space. Let's also take a look at how this setup is done. So under the simulation template shared from the simulation team, you can already see all the settings are already done. For example, the material properties are set, the boundary conditions for the occupants, external walls, internal walls, ceiling, floor, windows, and all the other conditions are already set. For the first approach, we would need to actually vary the temperature of the floor alone. To do this, we'll make a copy of this project into our own dashboard so that we have this template unchanged and can be referred at any point of time. Let's copy this project into our dashboard. We rename this project as design team and hit the copy project button. Once when this project is copied to our dashboard, we will have a separate version of this entire project so that we can edit or modify the configurations and run additional simulations based on the requirements. Now the project is copied into our dashboard and we have a separate copy of it. Let's go back to the simulation template. And now what we need to do is to change the floor temperature according to the approach 1. To do this, you can still keep the simulation template unchanged and make a duplicate of the entire setup. Once when we duplicate the entire setup, we will get a copy of the simulation template which is shared with us. Here we can go ahead and change the boundary conditions and start running the different configurations. For example, we'll click on the floor temperature. We would like to simulate the floor temperature from 20 degrees Celsius and start a simulation. You can also notice that we don't need to consider any other setup parameters before running this simulation. This is because the simulation team has already set up a perfect setup of this case so that we can use it without any changes. Now we have started a simulation with a floor temperature of 20 degrees Celsius. Again, we can do the same by simply changing this parameter again. Let's say we go for 24 degrees Celsius and then start a run 2. We can start as many number of simulations as we would like in parallel. So you can go ahead and go up to 30 degrees Celsius, start other simulations. Once when all these simulations are started, they are going to run in parallel and they are going to run in the cloud. So you don't have to wait for the simulation to be done, but you can start approaching the second and the third design criteria or the design approaches. To make sure we are going to the approach 2, we'll again duplicate the simulation template. And this time, we are not going to change the parameters of the boundary conditions, but we are going to change the geometry itself. To do this, you can click on the geometry, and then instead of the base case, we're going to select the approach 2. And now the domain or the model is actually exchanged. And here we might need to actually add a little more details to the simulation. On the simulation tree, you can see there are red circles for the material properties and the boundary conditions. So we need to fulfill them before starting the simulation. Please keep in mind that all the simulation settings for these particular boundary conditions are already preserved. So you don't need to set these from the scratch. Let's go step by step. As a first step, we need to set the material properties to the fluid domain. And then we get to the boundary conditions. Here, we already have the settings for the occupants and the other boundary conditions. We just need to select all the faces that corresponds to the occupants here and save them. We need to do the same for all the other boundary conditions before we start the simulation. Once when all these boundary conditions are assigned with the proper faces, we will have a new design that can be simulated. And here, as you can see, for the approach 2, we have 4 radiators instead of 2. For this approach 2, we'll be looking at the radiator temperatures of 60, 30, and 40 degrees Celsius. So you can directly start a simulation with this particular radiator temperature, and then again come back to the radiator setting and change the temperature here and start additional configurations. This way, you now have a lot of configurations running in parallel. Let's imagine you have waited for like 2.5 hours to 4 hours for the simulations to be completed. So at the end of 4 hours, you will get the results for all the configurations that you have started. And now let me get back to the approach 2 and approach 3 where we have already have the results. So for approach 2, we have 3 different configurations, and for approach 3, we have 2 different configurations that have already been finished. Let's get back to this slide and see what these configurations have produced in respect to the thermal comfort of this indoor space. We have the results for all the configurations. So now it's our time to actually check whether we are satisfying the design criteria across these configurations. And considering the first approach, we already see that out of these 12 simulations, we are matching the design criteria for two different set of configurations. The first configuration being the floor at 26 degrees Celsius and the surface temperature of the radiator at 40 degrees Celsius. Here we achieve a room temperature of 24.3 degrees Celsius, which is in line with the design criteria, and as well as the PMV, which is minus 0.3, which is in line with the design criteria. We also find out that another configuration is also matching the design criteria, which is the floor is kept at 28 degrees Celsius and the radiator temperature is at 30 degrees Celsius. So we have already found a different set of solution for this indoor space that can be used to manage the thermal comfort. Let's also take a look at the other approaches. So with the approach 2, where we have 4 radiators instead of 2, and without any floor convection, we have 3 different results. Here again, we have simulated that with 3 different outputs from the heat pump at 30 degrees Celsius, 40 degrees Celsius, and 60 degrees Celsius. Here we see that we only achieve the design criteria with the 60 degree surface temperature of the radiator. Although it satisfies 2 of the important design criteria, we are well over the heat pump output criteria. So this approach can be easily neglected or easily cancelled from the list of design configurations that we would need. Let's take a look at the approach 3 as well. For the approach 3, we did increase the surface area of the radiator and also doubled the layers of the radiator. Here, we did go with a lesser temperature for the heat pump output to match the design criteria, that is at 30 degrees and 40 degrees. When checking the results from these cases, we see that the approach 3 has a case where the design criteria is totally fulfilled. That is, with a 40 degree radiator surface. We achieve a temperature at the average of 23.56 degrees Celsius and also minus 0.3 for the PMV, which is all in line with the design criteria provided from the simulation team. And hence, this can be justified as an optimal design that can be used for this particular indoor space. This way, we will be able to actually make the concept phase validated using CFD so that you can easily pick up the optimal design for your heat pumps, and also the number of radiators or the surface area of the radiators can easily be tested, and all these concepts can be validated. All right, but we can also take a look at how the optimal design looks like with respect to temperature and also the PMV results. So just as the base case, we are comparing the temperature at the human head level. And here you can already see the temperature is distributed pretty uniform. And it ranges between 23 to 24 degrees Celsius, which is again in line with our design criteria. Also, the PMV results shows that the thermal comfort is slightly near the neutral regime of the thermal comfort, which is somewhere around minus 0.3. Hence, we already found out the optimal design from these 17 different configurations using CFD within 3 to 4 hours of simulation time. Thanks for listening until now. Now we'll focus on some of the questions from the participants and try to answer them within this session.
Ajit, thank you so much for that demonstration, and to Noor as well. Really interesting insights, Ajit, there about correctly sizing heat pumps, which are at lower temperatures than traditional gas-fired central heating. I think there's definitely some really good insights there, and the fact that you can do multiple simulations and compare them on the cloud in SimScale gives engineers a real ability to look at thermal comfort on a more spatial level, which is really interesting, that they might not get from thermal modeling. So thank you, Ajit, for that. Ajit, did you get the question we had about the mesh and the CAD?
Yeah. Can you please repeat the question, Nagman? Yeah.
Absolutely. So we have some questions coming in, and if you're online, please start posting your questions using the questions pane. So the first question is, can we use our custom generated mesh, or is it essential to start with the CAD data in SimScale?
That's actually a good, interesting question. I mean, there are a few options that you can use your custom mesh. We do support like a .met format for the meshing. So if you have your mesh converted to this particular format, you can simply import that and use that as your fluid domain instead of using the CAD geometry. But what we actually recommend is that when you have the CAD model inside SimScale, you have the entire autonomous meshing that can actually work perfectly. And you also have the option to actually edit your CAD within SimScale. When you have your CAD model in, you can simply increase the surface area of the radiators or even delete or add new bodies to the geometry and then start simulating other scenarios. So it is preferred that you bring in the CAD model, but you still have the possibility to load your own mesh also.
Okay, great. And maybe Ajit, just very quickly, you're talking about geometry. How easy is it to, you started off with a case where you had, two radiators of a certain size, and then you increased the radiator size, and then you added more radiators. Making those changes, how relatively simple is that for engineers to do?
Sure. I think for this question, I'll try to share my screen or just to answer this question in a top level. I mean, we do have something called a CAD mode within SimScale, which can be used when you upload the CAD geometry. So when you go on to the CAD mode, you can actually do some basic operations that are available for the CAD mode. So let me bring up my screen. So I hope the screen is on from my side now.
It's on. Thank you, Ajit.
Yeah, sure. So when you have your CAD geometries already imported into SimScale, you do have the option to actually edit that in the CAD mode, as I mentioned. So when you press that, it'll take you to the CAD operations scene or the scenario where you can do some basic operations like doing a Boolean, doing a transform, translating the model, translating the radiators, or even simplifying the bodies or finding interferences. So as you can already see on the left, I did use this CAD mode to delete some unnecessary faces from the CAD model to make it ready for the simulation. So the question which Nagman asks is like how easy it is to actually modify the CAD to increase the surface area. So for example, we can see, let me hide these two faces. So we have the scenario where the radiators are actually smaller in surface area. So if you want to increase the surface area, you can simply click on the face that you want to actually move. Select the move operation from the top operation panel, and then you can either set a distance or even set an up to entity operations, and then you say, okay, I need to extend the radiators until this face on the other side. I think it'll be clear if I hide this one. So I've selected this face and I'm going to move it until this particular entity. Sorry, I think I had to select. I did select the wrong faces, sorry. So yeah, so I'm moving this face up to this entity and you can press apply. It's going to take like a few seconds and then that will be done already.
I mean that's great to see that in SimScale you can make these geometric changes. You don't have to keep going to your third-party CAD tool and then re-import. So that's really great. Thank you, Ajit. Let's take another question. So users are asking, is it possible to measure in which case we have the lower power demand? So this is something we talked about, power output. I know it is possible. Maybe just give a quick response to Maurizio for that question.
There are two approaches that you can actually give. It depends upon the inputs that you get from your specifications, right? So for this particular case, what we did is like we took the power, we actually gave that as an input as a temperature on the radiator surfaces. But what you can also do is you can set a boundary condition where you can directly set the power of the radiators. So this way, you don't have to just set a fixed temperature, but you can put heat flux on the radiator faces. So for example, you have 30 watt per meter square of heat generated by the radiators. This can also be set as a boundary condition. So this is on the pre-processing side of the power input. And on the post-processing, you can actually derive the temperature difference from the ambient condition, and the power can be easily calculated from there. I hope that answers your question. Yeah.
Yeah, thank you, Ajit. We have a few more questions to get through quickly. I'll try and get through all of them. So just very quickly, I know you touched on geometry earlier as well. Nikhil's asking what type of file, this is geometry file, can be edited in SimScale, IGES, STL, or any 3D model?
That's actually a good question. So within SimScale, we do support quite a lot of native file formats, such as Parasolid, or you can even bring in directly from SolidWorks, Autodesk Inventor, Rhino, CATIA, and also some general formats, as you mentioned, like IGES, STL, and other file formats, which can be simply dragged and dropped here. So when you drag and drop here, anything that is inside SimScale can be easily edited using the CAD mode.
Thank you. We have another question. Someone's asking, can you rewatch this webinar? Yes, Aditya, we will send a recording of this webinar to everyone. Give us a couple of days and you'll get the recording to this. Ajit, we have a question from Siva Kumar on how to extract the fluid domain in the setup for the model.
All right. Yeah, for this particular model, what we did is we did extract the fluid domain. So what you're looking on the screen is actually the fluid domain. So in case if you have the solid wall, which is the external walls of your domain, you can again go to the same thing. So you can go to the CAD mode. And then here inside the CAD mode, you do have certain options to extract the fluid volume. So the first option here is create flow volume, where you can actually put an enclosure on top of your geometry. Simply like this, or you can also go with an internal fluid volume analysis, where if you have the solid wall, you can select all the bounding faces. For example, if you have this face with a gap or a hole, then you might need to select the bounding faces as your boundary faces here, and then click apply. This will generate the fluid volume for you.
Thank you, Ajit. Let's take one more question, last question, and then we'll wrap up with some summary comments. Great question from Clement here on, can we do an air conditioning simulation with the same setup? So I guess what Clement might be saying is here we're looking at thermal performance and looking at temperatures by adding heat into the space. Could we do something similar where we're trying to cool the space? I assume this is what Clement is referring to.
Sure. That's a good question again. So in order to actually include the HVAC systems or the air supply that you want to do, you might need to actually design the HVAC ducting, something similar to what you see on the screen. So if you have the ducting and the diffuser already modeled in the model, so you can select the faces and then simply use that as an input under the boundary condition. So for example, we go for velocity inlet, and then we say, okay, the HVAC system is working at a particular volumetric flow rate. So for example, 0.01 meter cube per second, and then you can apply that to the ducting here. And this will also be counted as a part of the simulation when you actually start the simulation.
Thank you. And Clement, if you had any more questions, feel free to get in touch directly to discuss a particular project. Final question, Ajit, from Aditya. Can the same setup be determined for radiator sizing of a vehicle?
This can definitely, yeah, this can definitely be done. I mean, instead of actually importing the office room or a room geometry, if you have your car model or the automobile model imported, if you have a closed volume, then you can be simply using the same setup for your automobile hatchback also.
Great. Thank you so much. Okay, fantastic. Thank you, Ajit, for the fantastic technical demonstration, and thank you everyone for your questions. Let's wrap this up. I hope you find this interesting. If you if you're interested in getting to know more about SimScale and how SimScale, the platform, and us, the SimScale team, can support your projects, you can get in touch directly with us through our website and request a one-to-one demo, or contact us directly at sales@simscale.com. Please feel free to post any more questions. We'll end the webinar here, but stay on, keep it online for a couple of minutes in case you want to post any more questions, and we can get back to you after this. Ajit, I think it was a really interesting topic. I mean, heat pumps are very topical right now. Everyone's trying to still find the right way to size and install them, and you're always hearing stories in the press and the industry press as well. When they're not correctly sized and installed, they tend to consume so much more energy than was predicted. So this is very timely. Thank you. One other comment I would say is, some of you might be using energy thermal modeling software to evaluate the thermal performance of heat pumps, especially when it comes to more of a time series analysis. So how much heat and thermal comfort they provide, for a certain number of hours in a certain occupied period in a room. That's fantastic. Where CFD comes in is a lot more detail in the spatial distribution, right? The spatial analysis of temperature and thermal comfort, because the energy thermal modeling tools can't give you that kind of output. So this is especially important to understand. A lot of the time we see people or engineers and designers, they replace the central heating system with a heat pump system, but it doesn't provide the same level of thermal comfort, because obviously the radiators are being supplied with much lower temperatures, and that space needs a lot more heat to meet the required thermal comfort criteria. And also the spread and distribution of heat and airflow as well, how that interacts in the space is really important, and you can only get those answers with CFD. So Ajit, thank you once again. Encourage everyone to get in touch with us. Ajit, any final comments from your side?
Thanks, Nagman, and thanks everyone for the listening. So if you want to get in touch with us, as Nagman mentioned, you can simply go onto the website and contact us, or use this email ID to reach out to us. Thank you all.
Thank you all, and have a good day. Bye.
Bye-bye.